What is a surface integral? Well, there are two different types, one with a scalar ds and the other one with a vector ds. Vector one is more important, but we'll do the scalar version first today. Okay, and next time we'll do the vector version. But what is it? What does it mean? Let's just think about this. Say we have this type of looking can, if you will, aluminum can. Okay? But this can, when we are finding the mass of this can, so it's empty inside. These are just purely surfaces. Okay? But then the can does not have a uniform density. Think of this as a density function. Okay? So it's proportional to z, meaning it gets heavier as you go up. So this bottom surface does not weigh anything. It's z density of 0, so it's just there, but it's weightless. This side gets heavier as you go up, and this side right here, of course, this part is heavier than this part. You know what I'm saying? Then what would be the mass of the whole thing? Is what surface integral is. Okay, so let's think like that. Okay, so if we want to calculate, let's just say theory, let's get theory out of the way, surface integral over certain surface, and then f of x, y, z, let's think of that as some kind of density function over ds. Okay, now then we have to figure out what that ds is. Okay, that s, surface s, is given by our two variable vector function, and we've been doing that for the last few days, right? It has x as a function of uv with the I vector, and then y as a function of uv with a j vector, and z as a function of uv, parameterized surfaces that we've been dealing with, right? Then how the heck do you find this ds? And we did it like this. You take a partial derivative with respect to one variable, and you cross that with partial derivative of r with respect to the other variable. And then dA here, du, dv. Okay, now, once you have that, that goes in here. You get it? I'm gonna push this thing down a little more. So this surface integral, actually I'm going to bring it down here. Why don't I do some house cleaning and rearrange this whole thing? Oh, no. I need more space. Can I push? Yeah. I never give myself enough time. I mean, enough space. What am I doing? I'm losing it. Okay. So once you have figured that out, then this thingy becomes double integral over that two-dimensional region. In this case, that d is this bottom thingy. Okay? D, wherever this u and v reside, and f of xyz. Now that xyz now becomes in terms of u and v, so you plug those values in. So x with a function of uv and y with a function of uv, and z with a function of uv. Okay, and then you attach that ds here. So partial with respect to u cross partial r with respect to v, and then we have dA. Okay, that looks daunting, and it's a complicated process. Okay, let's take an example, shall we? Whoa, what happened? Okay, so we have this c and ds, and s is given by this. So we have three different s's. S1 is the side, lateral area, and S2 is this bottom area, and then S3 is the top area. Okay. Alrighty then. We have to parameterize this S's, right? Let's start with this one. Okay. How can we parameterize this? Ideas now? We've been doing this for a few days, so should we go to cylindrical coordinate? Yeah. I mean, once you see a cylinder, why wouldn't you do cylindrical coordinate? So cylindrical coordinate has R, theta, and Z, except R is fixed. Our radius is 1. You know what I'm saying? So this will be a function of theta and Z. You good? Somebody tell me how to parameterize this. And don't be shy. Say it with conviction. Oh no.
Cosine theta, sine theta, and then Z.
Of course, cosine theta for x, I, and sine theta with j, and then just z variable for k. Good. You feel it? Between these two, you create a circle. So you have 1 degree of freedom around the circle here, and then z gives you another degree of freedom, so you create this cylinder. Are we good? Can you think like this? Okay, of course, this is not a uniform cylinder, so we have to think about that. Limits, you remember, limits of integration is the tough thing in this business, but at least we got the surface. So now, then we'll take a derivative with respect to theta. Okay, so that becomes negative sine theta I vector plus cosine theta j vector plus 1 k vector. Oh no, 0 k vector, because we are differentiating with respect to theta. And then with respect to z now, so this thing becomes 0 I vector plus 0 j vector plus 1 k vector. You with me? Now, so we take with ds, which is a cross product of these two, right? Imagining I, j, k, so with the I, this is cosine, right? So cosine theta I vector, and j negative 1, and you have this. So we have becomes plus sine theta j vector. You with me? You with me? Okay. And then k vector, this thingy, so 0. So this is it. And then we have to take the magnitude of this, and then we have to put d theta dz. So far so good? Okay. Magnitude of this is just cosine squared plus sine squared. So it's just this d theta dz, isn't it? Say yes. Okay then. Let us integrate. So for the surface 1, let's put it right here. Double integral of surface 1 of z times the s, capital S, becomes double integral now. We have to start with z first, looks like, and then we have dz and d theta. That makes sense to you? And then z varies from what to what? Let's look at this picture. Z varies from down here, right? From 0 to that thingy, right? Z is equal to 1 plus x. So far with me? So z will vary from 0 to 1 plus x, but what is x in cylindrical coordinate? What's our x here? This is our x. You get it? And that's the z. So our x is just cosine. You know what I mean by? Good. Okay, so this is 1 plus cosine theta. I'm going to zoom in to write this in. You get it? And then theta can vary from 0 to 2 pi. The limits of integration is very tricky in this business. And then why are we keeping z as our variable z? Because this z is also our parameter z. If I changed this to u, then this would have been u. You get it? Who's confused? Okay, after this, it's a downhill. 0 to 2 pi of z squared over 2. And then we evaluate this from 1 to 1 plus cosine theta, and then the theta, right? Say yes. Okay, let's plug it in. So we have, do you want half outside or leave it in? Leave it in. So we have, this thing is square, so we have 1/2 plus cosine theta plus 1/2 cosine squared theta. Too much algebra? That is equal to, now how do we deal with this cosine squared theta? That is 1 plus cosine 2 theta over 2 now, isn't it? Okay, so 0 to 2 pi of, so 1 plus over, do you see 1/4 that's getting combined with this one? Plus cosine theta plus 1/4 cosine squared theta. Who's confused at this stage? That algebra was a little tricky. You with me? Okay, let's evaluate. How much time do I have left? If I did the whole thing in my head, 3 pi over 2. I totally copied that from the book, because I'm pretty sure you can evaluate this integral, right? But cosine squared, ooh, I screwed up. That's cosine 2 theta. Okay? So far so good? Okay, let's do S2. S2 is easy. Let's just think about it. Here's z ds of S2. See, z is equal to 0 on S2, isn't it? So this whole thing is 0. And integral of 0, of course, whatever it is, it's always 0, isn't it? Done. Okay, so S3 is the only thing left, and it's slightly trickier than S1, not really. Okay, S1, S3. Okay, I'm going to use capital R because something tells me I'm going to need that R. How should we parameterize this? We have some surface, but it's slanted and it's a circular region. Let's just think about X and Y. X and Y first. So R of, should we go polar? I mean, why not? If you see something circular. And then for X and Y, we have R cosine theta, I vector, and then R sine theta, J vector. That much good? The only thing we have to worry about is Z. We have to give some elevation, otherwise this is a flat, this is S2 at the moment if I put 0 here. You know what I'm saying? So how do I give this elevation like that to tilt it? Somebody give me a brilliant suggestion, and it's staring at you right here. This last vector is Z. And I have a relationship between z and x here. Z is equal to 1 plus x. You get it? So I need to put for this z 1 plus, don't write this yet, x k vector. Except what is x? Somebody just tell me what x is. It's not a trick question, it's staring at you.
R is theta.
This is your x, you get it? So x is just r cosine theta, so let's substitute that one in. And then k vector. You feel it? Are you somewhat with me? Okay, now once you have that, then it's relatively downhill. First, we take a derivative with respect to r, and this thing becomes cosine theta I vector plus sine theta j vector plus cosine theta k vector. So far so good. Derivative with respect to theta now is this thing becomes negative r cosine, r sine theta I vector plus r cosine theta j vector, and then plus or minus r sine theta k vector. Still with me? Okay, now ds is cross product of the two, so ds is the magnitude of cross product of the two. So let's imagine I vector this thingy. So we have negative r sine squared. So far so good. And minus r cosine squared. That's just negative r. Are we good? Okay, and j vector, negative of this, let's just go this way first then. This, so we have negative r sine theta cosine theta, and this way positive r sine theta cosine, oh, it's 0, so that died. Okay, and k vector. So we have r cosine square plus r sine square. Also, that's just r, isn't it? You with me? Okay, so this thingy is just the magnitude of this. So r common, so r square root 2a. You with me? Common factor r out and 1 squared plus 1 squared a. Okay, then we can evaluate the integral. So s2, s3, z ds becomes, okay, let's think about it. Z was up there, this thingy, this computer. So 1 plus cosine, now we substitute this value, 1 plus cosine theta. Okay, the z, ds is this thingy, so we'll put few. Now just write it. R square root 2, and then dr, the theta. So far so good?
Why is it, isn't it r root 2 r dr d theta because of the dA? Or
No, not really. That's kind of a baked in.
okay.
Yeah, that when we cross product, see that r dr d theta, actually we found it through this process. You know what I'm saying? That slant just gives you the factor of root 2, a little more. But can you imagine if this was not there, that root 2 was not there, that's just r dr d theta, which is our usual dA. You know what I'm saying?
Yeah.
Yeah, that 45-degree tilt give us that factor. I think I screwed up. I am missing R here though, right? So I'm gonna squeeze that in. 1 plus R. Are you with me? Limits of integration. The radius. Now we are on R theta plane, right? So radius will grow from 0 to 1. Theta is 0 to 2 pi. So that one was easy now, wasn't it? So this is from 0 to 1, and this is from 0 to 2 pi. Good. Let's just distribute. So we have root 2 out here, 0 to 2 pi, and 0 to 1. And then we'll have R plus R squared cosine theta. Oh, I guess the integral is easy. dr d theta, eh? And that will be root 2, 0 to 2 pi, and this thing becomes R squared over 2 plus R cubed over 3 cosine theta. From 0 to 1 and the theta. Moving down, root 2, 0 to 2 pi. So this thing becomes just 1/2, and this thing becomes 1/3, eh? Cosine theta, eh? Okay, and almost there, home stretch. So this is 1/2 theta and plus 1/3 sine theta, eh? Okay, 0 to 2 pi. And these are coterminal angles. These things don't contribute much. The trig functions between 0 to 2 pi always gives you 0 because they are coterminal angles, so it's just 2 pi here, right? So we have root 2 times pi. And that's it. Altogether, so your entire surface of z ds, and integrals do add, right? So we have that thingy. I'm going to put that one at the end. Root 2 pi, and our answer from earlier, which is 3 pi over 2. 3 over 2, common factor. How about that? Good. So we are continuing with the surface integral now, but this time with the vectors, okay? Because previous example, we found the scalar, ds, right? And then we took the surface integral. Now it's more of a vector. So the concept here is if there's some kind of vector field, some flux, that's passing through certain surface, how much of the flux does this thing catch? Okay, so let's get that. You're not doing E&M yet in your physics classes, right? Are you? This thing actually has huge implication in Gauss's law later, but just think of some kind of field coming out of this thing. Okay, let's say there's a source inside this looking surface with a bottom, and then how much is the total? And so what's conventionally what's coming out, you count it as a positive, and what's going in, you count it as negative. Okay, so it's because we decide to orient this surface ds as an outward. Okay, now so let's first start parameterizing this. So we have S1, and then S2 is the bottom surface. Okay, so top surface is this, and bottom surface is just a disk on XY plane. Okay, so let's say S1. Okay, let's use R, and then we'll just use X and Y as our parameter. How's that? So that we'll have X, I vector, plus Y, J vector. Still remember this? You remember forgetting this? And our Z is this, right? Because we use two variable in parameterized surface. So we have 1 plus 1 minus 1 minus x squared minus y squared. And that's our k vector. So first of it. Okay, so way we calculate ds is we take a derivative partial derivative with respect to these parameters, variables. So with respect to x, then this thing becomes I vector, this thing becomes 0, and this thing becomes negative 2x, eh? Still with me? And we take a derivative, partial derivative with respect to y, the other. That's ugly. Hold on. Variable. So the first one becomes 0 vector. Second one becomes j vector. And then k becomes 2, negative 2y, k vector. So far so good. So now our ds vector, big capital S, is a cross product of this, right? Okay, so I, j, k. So with I crossing this out, this is a 0, and then minus, so we have 2x I vector. With me so far? And then j, negative 1. This. So we have, make that positive, 2y, j vector a. And then the other one is 0. And k, you have 1 and a 0. So we have plus k vector. And then dx dy. With me? Say yes. Now, then, usually we took a magnitude of this in order to do the surface, right? This time, we're just taking a dot product with this and our vector function f. Okay, I'd like to simplify that. So f dot ds. Okay, what is f then? Well, f is this thing, y, x, z. Okay, so f is y, x, and z, and dot that with 2x, 2y, and 1, and then dx dy. Good? Say yes. So what we have is 2xy and plus 2xy, so make that 4xy plus z. But what is our z? This is where we have to substitute. I could have substituted earlier here, but remember my z, we're using this thingy. This is my z. You know what I'm saying? So my z is 1 minus x squared minus y squared. Shove that in here, like that. So what we really have is 4xy. Oh, did I use a vector symbol here? I mean scalar now, because we took a dot product. So we have 4xy, and then plus 1 minus x squared minus y squared, dx dy. So far so good? Say yes. Okay. Now we are ready to take an integral. So shoving it in inside the integral. So over S1, f dot ds, we are doing S1 first. Okay, that is equal to, now we look at this and say, should we go polar? Yeah, right. And then our region here is nice and circular, so why wouldn't you go polar? Okay, so let's see, this one is for, ooh, somebody tell me what xy is in polar coordinate. Oh no, you forgot everything over spring break, then yeah. What is x in polar coordinate?
R cosine theta.
R cosine theta, and y is?
R sine.
R sine theta, so we have r squared sine theta cosine theta, eh? Say yes. Okay, and then plus 1 minus, and that is r squared, eh? And then we have additional r here, the r, the theta. Remember that? And then our R will vary from, now we have to decide, okay, looks like this is 1 right here, isn't it? Do you feel that? Oh no, so 0 to 1 and theta will vary from 0 to 2 pi. Whew. Okay. So theta from 0 to 2 pi. And so we have really R cube, correct? So it becomes R to the 4th power, and that 4 cancels. And sine theta, cosine theta. Should we convert that into sine to theta? Yeah, so we put 1/2 and sine to theta. Either that or use sub. I always like this way. Okay, plus this thing becomes R, so R squared now, so R squared over 2. And this thingy was R to the 3rd power, so it becomes R to the 4th power now, right? 0 to 1, and then we have the theta. With me? Okay. Once you substitute, this just becomes 1, so what we have is 1/2 sine to theta. Good. And this is 1/2 minus 1/4, so we have 1/2. I mean 1/4. Good. Here, let's use our usual trick. This is trig function. This is going to become cosine, and then 0 to 2 pi. It's coterminal angle, they are the same thing, so this thing dies, right? So only thing that survives is this, theta from 0 to 2 pi. So this thing becomes pi over 2. How's that? Are you with me? Okay, then let's do S2. Our S2, change the color. Okay, S2 is a much easier thingy. Xy is equal to xi plus yj, and z used to be 1 minus x squared minus y squared, but instead we put 0. How's that? Very good. And I could have started with the polar here, but why? So with the derivative with respect to x, then you get 1 I vector and then 0, 0, such as this, right? And then the partial derivative with respect to y, you just get j, and the other two dies. Good. Okay, let's find ds. ds is a cross product of these two. What is the cross product of I and j? 1, 0, 0 cross 0, 1, 0. Do you see this is just k vector? I cross j is k, right? dx dy. Okay, now let's start it. So f dot ds, ds vector. And let's remember what f is. F is this, y, x, z, okay? Y, x, what's our z? This is our z right here. Good. I made a substitution. Started with just k vector 0, 0, 1. Is that thing 0 then? Yeah. Oh, that's convenient. So now S2 of f dot dx happens to be 0. So finally, so over the entire surface S of f dot ds is just whatever we got from S1, which is pi over 2. How's that? All good? Any questions before I move on to the next example? Okay, now we have a spherical surface. Okay, and then we have this kind of vector function. So whatever is coming out of this, and they actually, your book gave you this little sketch of this flux. Okay, now, so we'll do the same thing. We'll say R here. Should we go spherical coordinate now? So we have phi and theta. Good. So according to spherical coordinate, we have sine phi cosine theta I vector plus sine phi sine theta of j vector and plus cosine phi k vector, right? Oh, notice that the radius of the sphere is 1, so I did not put any radius in front. Good. So we'll compute ds. So partial derivative with respect to phi first is equal to, this thing becomes then cosine phi cosine theta I vector plus cosine phi sine theta j vector plus minus sine phi k vector, right? Okay, so partial derivative with respect to theta now is equal to, and this thing becomes negative sine phi sine theta I vector plus sine phi cosine theta j vector, and this one does not have theta in it, so 0 k vector, right? You with me? Okay, so ds is the cross product of these two. Okay, so let's imagine little I vector here. So we have this minus this. This is 0. So this, make that plus sine squared b, and then cosine theta I vector. You with me? And j vector, that's negative 1. So this is 0 minus this, right? Oh, minus, so make that positive now. So we have sine squared p and sine theta j vector. And then finally k, so this minus this. So this way you have sine phi cosine squared, and this way plus sine phi cosine sine squared. So do you see that you just get sine phi cosine phi? You with me? And then defeated theta, of course. Say yes. Okay, let's take a dot product now. So I will say f dot ds. What is my f? Z, y, x. Okay, this is a little complicated, so I'm going to write it down here. This is my x, and this is my y, and this is my z. Okay? So z, which is cosine phi. Good. And then y, sine phi, sine theta. With me? And x, I'm just copying this z, y, x according to these things. X is sine phi cosine theta. Sine phi cosine theta. You with me? And then dot that with, oh, that's a lot of writing. I'll just write ds. This ds. Okay? Okay, let's dot it. So what we are going to do is multiply cosine phi to this Okay, so we'll have sine phi, sine square phi, cosine phi, cosine theta, sine square phi, I'm going to need a parenthesis, and then cosine phi and cosine theta for the first dot product. And then second one, I will have sine cube phi, right? Okay, so second one plus I will need this thingy times this thingy, so I need sine cube phi and sine squared theta. Say yes. Okay, plus the last thing, this thingy times that thingy, that's sine squared phi cosine phi and cosine theta. And then the phi, the theta. Any questions so far? Okay. Okay. Now, do you see that this whole thingy and that whole thing is the same thing? They are like terms. Combine those two and shove it inside the integral. So I have s and then f dot ds will be, okay, now we are already in spherical coordinate, so we don't have to convert this thing in spherical coordinate, right? So our phi varies from 0 to pi, entire sphere, so theta varies from 0 to 2 pi, good? And then I will have 2 sine square phi, cosine phi, cosine theta, good? Okay, plus, and then I will have sine cube phi, and then sine squared theta, and then the phi, the theta. Whew. Are you with me so far? Okay, here is where we can make our lives little easier. Here's a cosine theta, and nothing else, no complication. So this will become sine theta, wouldn't it? And then I have 0 to 2 pi. So do you see that this whole thing will die? One color. Why doesn't it change the color? I had it change the color and it doesn't. Oh, now it's good. That's so weird. This thing will die. Do you see that? So all we have to do is now just integrate this. You get it? Say yes. Okay then. Which variable would you like to integrate first? There's no particular order. You can just do whichever you want. I'll just do whichever you want first. Do you want phi first or theta first?
Do phi.
Phi first. So how did we integrate sine cube phi?
You do phi and sine square phi.
This is 1 minus cosine squared times sine, right? Right, so what we have here is sine phi and then minus cosine square phi sine phi. Say yes. And then we still have to deal with sine square, which I will deal with later, sine square theta, and then the theta. Okay, now here. Do we know that this thing, I'll just do it. This thing becomes negative cosine phi. Good. Say yes. Okay, this thing is a u sub, isn't it? This is u and du. Eh? So this thing turns into plus, and this is 1/3 cosine q phi. Let's check. If I take a derivative, that 3 cancels, becomes cosine square, and then chain rule, negative sine. Yeah. From 0 to pi. And then we have sine squared theta d theta. Okay, let's substitute. So once you substitute pi, this thing becomes 1. Good. Minus 0. So we pick up 2, eh? Say yes. Likewise, exactly same thing happens here, right? Pi becomes, this time, negative 1/3. So do you see this? Okay, now we have to deal with this. So that thing is 1 minus cosine 2 theta over 2. Okay. So taking this out, what is 2 minus 2/3? That's 1 and 1/3, 4/3, right? So taking 4/3 outside, and we will have here 1/2 theta minus, that's 1/2, so will be 1/4 sine 2 theta, eh? Say yes. Okay, now once again, this we could have used that trick. This will die because 0 to 2 pi is coterminal angle. So only thing that contributes is this. So 2 pi in here, you just get pi times 4/3. So we have 4/3. I'm dividing 4/3 of pi as our final answer. How's that? Good.